Alright, we want to talk a little bit today about air resistance, which is really just drag. Okay, drag is the force that a fluid exerts on an object moving through it. Okay, force exerted by a fluid, on an object moving through it. Okay. And it's important to note that this force opposes motion. So it doesn't matter which way an object is moving. If it's moving through a fluid, this force opposes it. So if it's a boat moving across the lake, the force is against the motion of the boat. If it's an airplane moving through the sky, the force is against the motion of the airplane. If it's a skydiver dropping to earth, it's a force upwards against the skydiver falling. Okay? And so when the fluid is air, we call this air resistance. Creative, huh? So when the fluid is air, it's called air resistance. Okay. And the math that gets into this can get fairly complex in a hurry. Like, it has to deal with the shape of the object, the surface area of the object, how fast the object is going. Okay, but what we're going to say for now is air resistance increases with speed. That was odd. Air resistance increases with speed. And surface area. Okay? And so if we take these two things into account, we can completely explain the motion of a skydiver. By the way, you should look up a guy named Felix Baumgartner. He just jumped from 24 miles above Earth and broke the speed of sound as he fell back towards Earth. Okay, he got going really, really fast. You should take a look at it. Anyways, say we have a skydiver, jumps out of a perfectly good airplane, so he's pretty sad. Okay, but he's falling through the air. When he first jumps out of the airplane, he's got no vertical velocity, so the only force acting on him is gravity, and that means he's going to accelerate in this direction. Okay? But as soon as he starts to accelerate, he starts to have air resistance. So then air resistance starts to creep up this way. Now, the force due to gravity is still bigger than the force due to air resistance, so he still accelerates, but his acceleration is less. Okay, so now he's got a little bit less acceleration. But as he's getting faster, this force of air resistance keeps getting bigger. So eventually, what happens is the force of air resistance will exactly balance the force due to gravity. When this happens, okay, then the person doesn't stop falling, the person stops speeding up. So the acceleration here would be zero. These two forces exactly balance. Okay? So this is what's called terminal velocity. Terminal means ending, and velocity is speed and direction. So this is the final velocity of a falling object. And it occurs when the two forces balance. Okay? So it occurs when air resistance balances the force due to gravity. Now, we can change an object's terminal velocity. All we have to do is change how big this air resistance force is, and since that depends not only on speed, but also on velocity or on surface area. If the parachuter decides to pull his parachute, okay, well, he just increased his surface area a whole bunch, which means all of a sudden this air resistance force got really, really big. And that means his acceleration is also in that direction. And so that means he's going to start slowing down, slowing down, slowing down, slowing down. But as he's slowing down, his air resistance force decreases, 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 until again it returns to balancing gravity. But this time it'll balance gravity at a much, much, much lower speed. And so this allows the skydiver to fall to earth at a nice controlled descent and, you know, smack into the ground at a relatively low speed as opposed to death. Okay, so that's air resistance. Now I want you guys to combine what you've done in your lab and with air resistance, and there's a few problems in the book I want you to take a look at. They are posted on Moodle. If you have any problems, let me know. Good luck.